A, B, C, D, one, 0, 0, 0. Okay, so this belongs to you, this also belongs to you. Hence, their sum will also belong to you. This also belongs to you. Since this is the 2 by 2 identity matrix, and we know that in the matrix ring we are considering, this is the unit element. Since this is the unit element in our ring, we have from exercise 1 that U is the whole ring. That is, if an ideal contains the unit element, then it has to be equal to the whole ring. So you see what we have shown. If U is an ideal different from the zero ideal, then it has to be the whole ring. That means other than the zero ideal and the whole ring, there is no other ideal. And that's what we had to show. So this completes the solution to the 12th one, which is somewhat difficult. But the next one is even more difficult, the 13th one. Okay, so let us see what the 13th exercise is asking. In example 318, we discussed the real quaternions. If you remember, real quaternions turned out to be a division ring which is not a field. The only example we so far have of such a thing, the real quaternions. Using this as a model, we define quaternions over the integers modulo p, where p is an odd prime number. P an odd prime number. In exactly the same way, however, considering all symbols of this form alpha naught plus alpha 1 I plus alpha 2 j plus alpha 3 k, where alpha naught, alpha 1, alpha 2, alpha 3 are integers modulo p. I need some ink. So that means now our quaternions don't have real value components. If we call these things components, this alpha naught, alpha 1, alpha 2 and alpha 3, previously they used to be real numbers, they were real numbers, but right now they are integers modulo p. If you recall, integers modulo p, which is jp, it is the set of all congruence classes modulo p. These are not numbers, but they are congruence classes modulo p. There are p number of such congruence classes, and we have already seen that they form a ring, in fact a field, when p is a prime number. So this alpha naught, alpha 1, these elements are now these congruence classes. Each one of them is one of these congruence classes. Okay. And the fact that we are using real quaternions as a model means that the definitions of addition and that god awful multiplication, that one which is very complicated for real quaternions, here also everything is exactly the same, only the components are coming from, instead of the field of real numbers, they are coming from a finite field of integers modulo p. Now comes the first subdivision. Now there are two subdivisions. Prove that this is a ring Remember, the real quaternions were infinite in number. It was an infinite division ring. However, now the system will be finite because the coefficients or the components are coming from a finite set. There are p choices for each of these alpha i's. Okay, that's why they are saying it's a ring with p to the power 4 elements whose only ideals here also whose only ideals are 0 and the ring itself. Okay, so this is subdivision A. Now here this one is very difficult. It has 2 stars, 2 asterisks. Prove that this ring is not a division ring. Unlike the real quaternions which form a division ring, this is not a division ring. That's what we have to show. So we have 3 things for us to show. We have to prove that the ring is, the system is a ring with p to the power 4 elements, and the only ideals of this ring are the 0 ideal and the ring itself. and then we have to show that it is not a division ring. Okay, so let us go through the solution. Now part A, you may be thinking that we have to go through all the things that we need to in order to conclude that a system is a ring. We have to write all those things, but actually that's not the case. You recall quaternions, real quaternions. Real quaternions were just like this, right? Symbols like this where the alpha i's are real number, where we defined an addition. Addition was component wise and multiplication was somewhat complicated, but that also follows a rule, a pattern. And there I mentioned that you verify for yourself that the real quaternions form a ring. Now in that verification, if you have gone through that, if you have taken the pains of going through the calculations actually, you can notice one thing, that in those things, in those verifications, we have only used the fact that the real numbers form a field. Nothing else about real numbers we have used there. The only facts we have used are the field axioms. The fact that the real numbers form a field under addition and multiplication of real numbers. Now here also the components are coming from a field, a different field, integers not be, but nonetheless that is also a field. So don't you think that the same proof works in this case also? If we just write everything verbatim to what we have in that proof or in that solution or verification, because integers not be also form a field, real numbers also form a field. We haven't used any fact about real numbers which are special to real numbers, other than of course one thing. In showing that the real quaternions form a division ring, we used the fact that the ring of real numbers has characteristic 0. The field of real numbers has characteristic 0. That thing we have used. So we can write all these things like this. The proof that the given system is a ring is similar to the one involving real quaternions. Okay. Note that there means in that proof of real quaternions form a ring. Note that there we have only used the fact that the system of real numbers is a field, except in showing that the real quaternions form a division ring where we used the fact that the field of real numbers has characteristic 0. Okay, so the same proof works here also. I mean, at least the part where we show that the system is a ring. Since we use the fact that R has characteristic 0 to prove that the real quaternions are form a division ring, so that fact we will not use here because the integers mod p have characteristic p. It's not 0, it's a prime number. Okay, it's finite. Okay, now what else? So for us, that this discussion tells us that the system is a ring. But next what? It has p to the power 4 elements. Since in an arbitrary element alpha 2j plus alpha 3k, each of alpha 1, alpha naught, alpha 1, alpha 2, alpha 3 can take any of the p values, congruence class 0, 1, etc. up to p minus 1. The number of elements in the ring is p to the power 4. There are p choices for alpha naught. Independent of that, there are p choices for alpha 1, p choices for alpha 2, p choices for alpha 3. So by the definition of equality of two such symbols, which says that two such symbols are equal if and only if their corresponding components are equal, from that we get the fact that there should be p to the power 4 elements in the ring. Okay, so now we have to prove that this ring also has only the 0 ideal and the ring itself. Okay, this will take some effort. This we do in the next paragraph. So we start off just like the previous problem. Let U be an ideal of the ring. Since we haven't given the ring any symbol or any name, so we just keep on saying the ring. You know what ring we are talking about. So this is an ideal of the ring that is different from the 0 ideal and has no unit of the ring. We know about unit element, but what is a unit? We need to say that a unit in a ring is a non-zero element that has a multiplicative inverse in the ring. That is called a unit. One simple example is this. If you look at the ring of integers, there are only two units, -1 and 1. Multiplicative inverse of -1 is -1 because their product is the unit element, and multiplicative inverse of 1 is 1 itself. No other element has multiplicative inverse that is also in the ring. So these two are units in the ring of integers. Others are non-units. We will look at units and non-units more about them when we study Euclidean ring. That is there. After some sections we will get to that concept. So now the ideal we have considered is an ideal that is different from the zero ideal, and also it has no unit in it. What happens when an ideal contains a unit of the ring? Suppose U is an ideal in a ring R, and let U be a unit in U. Of course, R has to have a unit element, otherwise the definition of unit will not make sense. That means there exists a multiplicative inverse U inverse in R such that U inverse is equal to 1. Okay. Now note this. Now since U belongs to U and capital U is an ideal, so this product will belong to U. Then by exercise 1 we have the fact that U is equal to R. So if our ideal contains a unit, then it is automatically equal to the whole ring. To prevent that from happening, we have considered we have assumed that U has no unit. At the same time, okay, by the way, 1 itself is also a unit, so this assumption holds in itself this assumption also, that 1 does not belong to U. So that means we are considering this. Our ideal is not the zero ideal, it's also not equal to the whole ring. And we are actually assuming something which we have to show that this is not possible. That means we are expecting a contradiction. We will have to get to a contradiction. We are going to go towards that. Okay. Now since U is different from the zero ideal, there will be a non-zero element. Let us choose a non-zero element A, which is A0 plus A1i plus A2j plus A3k in our ideal U. Now you have to carry out these calculations. They are not very difficult, they are rather easy, but you have to be careful. IA plus AI. Okay, IA plus AI is equal to minus 2A1 plus 2A0I. Just like that, JA plus AJ is equal to minus 2A2 plus 2A0J. Is it J? Oh, have I made a mistake here? A0 J. Okay, let me just see. If I multiply this by J, then I have A0 J. Yes, okay, 2A0 J, and Ka plus Ak is equal to minus 2A3 plus 2A0 K. And these elements belong to U. Why? Oh, you may find one more thing confusing. I think I should make this more clear. You may question, what is I? When we studied real quaternions, do you recall we made an identification of these symbols with some elements? That is, for us, I is equal to 0 plus 1I plus 0j plus 0k. It is that thing, this I. If you find it confusing, then I can change it. I can call it I prime, j prime, k prime, where I prime is 0 plus 1I plus 0j plus 0k, and like that. J prime is 0 plus 0I plus 1j plus 0k, and k prime is 0 plus 0I plus 0j plus 1k. Okay, now it's okay. So these are again elements in the original ring, in our ring, and so we can multiply these elements I prime with A, and we can add their products. That gives us these elements, and they all belong to U. Note one more thing, that this 0, 1, 0, 0, these are not numbers, because now our components are coming from integers mod p. So this is the congruence class 0 modulo p. This is the congruence class containing 1 modulo p. It's understood that this is the thing, because this is the 0 element in the ring of integers mod p. This is the unit element in the ring of integers mod p. And since those elements we usually write by 0 and 1 respectively, so there is no problem actually. Just keep in mind that these are not numbers. Okay. So now these three elements, minus 2a1 plus 2a0 I, minus 2a2 plus 2a0 j, minus 2a3 plus 2a0 k, these elements belong to U, the ideal. Hence, a0 plus a1i, a0 plus a1i is nothing but minus 2 inverse I times I prime a plus ai prime comma a0 plus a2 j is equal to minus 2 inverse j prime a plus a j prime comma a0 plus a3k is equal to minus 2 inverse k prime a plus a k prime. These elements also belong to U. What is 2? What is this 2? This 2 indicates the fact that we are adding a naught with itself, a naught plus a naught, it is that 2. This 2 is the number 2. Or if you want, you can also think of this 2 as congruence class modulo 2. The result that the interpretations that you get may seem different, thinking of a naught plus a naught as 2 a naught and thinking of 2 a naught as this. They are actually the same. You can see, you take, because after all a naught is going to be some congruence class, right? So if you are multiplying these two congruence classes, according to your definition, what do you get? 2m, which is what? M plus m, which again according to the definition of addition of two congruence classes, m plus m, which we generally write as 2m. So whether you interpret this 2 as number 2 or congruence class 2, the end result is same. So there is no confusion here. And congruence class 2 is not a zero element in the integers mod p. That's what we have to write. Note that in bracket 2 is not equal to 0 because p is odd. What is the meaning of this? You see, 2 is an element in JP. Actually, this 2 is this class, congruence class modulo P, which contains the integer 2. This statement just means this. Why is this true? Because if we had 2 is equal to 0, then that would mean that P divides 2. Because 2 has to then be congruent to 0 mod P, that means P has to divide 2. But P is a prime, then a prime can divide 2 only if the prime itself is 2. That is the only case. But it is given that P is an odd prime. P is not the even prime 2. So that's why oddness of P allows us to conclude that this is a non-zero element in the field JP, and that's why it has an inverse. It is that inverse. Okay. So now these elements belong to U. This one, and this one. So their sum will also belong to U. Hence, okay, let me write here A naught plus A1I plus A naught plus A2J plus A naught plus A3K. This belongs to U. But what is this? If you take these elements together, A naught, A1I, A2J, A3K, you get the original element A plus 2 extra A naughts. That means this is 2 A naught plus A. This belongs to U, which implies but A itself is in U, so that means 2 A naught must also belong to U, which implies 2 A naught belongs to U. Okay, since U is an ideal, we have A naught equal to 1 A naught, which is equal to 2 inverse 2 A naught. This also belongs to U. 2 is already invertible in the ring of integers mod P that we have seen. So A naught now belongs to U. Now what is A naught? A naught is an integer modulo P, and it belongs to U. Note that U has been assumed to be an ideal that has no unit of the ring. No unit of the ring means, in particular, every non-zero element of Jp is a unit of our ring. Why? You see, if I consider this element, say I consider 2 congruence class modulo P, which contains 2 plus 0i plus 0j plus 0k. Suppose I consider this element, then I have 2 inverse I have these 2 elements in our original ring. If I multiply them, I get this. You can verify. Which is nothing but the unit element in the original ring. This calculation shows that I can identify this ring element with this element itself. That's what we mean when we write A0 belongs to U. We are thinking of A0 as not just A0 but A0 plus 0i plus 0j plus 0k in that sense. So any non-zero element we consider in the field as an element in the bigger ring, it is a unit, but our ideal does not contain any unit. So that means this A0 cannot be non-zero, it has to be equal to 0.